So in the last video, we saw what is meant by a matrix associated to a linear transformation once we are given an ordered basis of the domain and the codomain. So in other words, if T is a linear map from V to W, and if alpha is an ordered basis of V and beta is an ordered basis of W, we defined the notion of a matrix associated to T with respect to alpha and beta. Now we are familiar with matrices. We know that matrices can be added. We can talk about scalar multiplication of a scalar with a matrix. We can also talk about product of matrices. So the goal of this lecture is to explore if something similar can be done with linear transformations, and if something similar can indeed be done, is it compatible or in sync with what we know about matrices, because after all we are able to associate a matrix to a given linear transformation. So let's begin. So let V and W be vector spaces. So our first question is, can we talk about the sum of or addition of two linear transformations S and T between two vector spaces V and W. So let V and W be vector spaces, and suppose S from V to W and T from V to W are linear transformations. We define S plus T, a function, a transformation from V to W to be S plus T of V is equal to, by definition, SV plus TV for all V in capital V. Note that SV and TV both are vectors in W, and therefore we can talk about addition of these vectors in W. Moreover, it is also important to note that as of now we do not know whether S plus T indeed happens to be a linear map. As of now, it is just a transformation, it is just a map, and yes, so the next proposition will tell us that S plus T is always a linear transformation with S and T as above. S plus T is a linear transformation. So let's give a quick proof of it. I'll just indicate one part of the proof. To check that S plus T is a linear transformation, we need to check that S plus T preserves both the addition and the scalar multiplication. Let's just check the addition part. So for V1 comma V2 in capital V, let's ask what is S plus T of V1 plus V2. We would like to show that S plus T of V1 plus V2 is S plus T of V1 plus S plus T of V2. But this by definition turns out to be S of V1 plus V2 plus T of V1 plus V2, which is equal to SV1 plus SV2 by the linearity of S plus TV1 plus TV2, which by the vector space axioms will be SV1 plus TV1 plus SV2 plus TV2, which is equal to S plus T of V1 plus S plus T of V2. We have just checked that S plus T indeed preserves the additive structure. So I will leave it as a check that S plus T of AV is equal to A times S plus T of V. And with this we would have established that if you are given two linear transformations S and T, we can talk about the sum S plus T. Right. We would also like to now see if we can talk about a scalar multiplication. As to be expected, it will be the straightforward definition that that we can give just like in the case of addition. So, let T from V to W be a linear transformation between vector spaces, and as usual our vector spaces are always real vector spaces. Here in this course, be linear transformation between vector spaces. Now, let A be a scalar, a real number. Then we define the scalar multiplication of A and T, which will denote by AT. This is a map from V to W. We define this to be AT of V is equal to A times TV. Now, observe that AT a priori did not have a meaning of its own. So, AT is just a symbol. AT is a function now which acts on V and gives you some vector in W. And what is that vector? We already know that T is a linear transformation. So, TV is a vector in W, and you look at the scalar multiplication of A with the vector TV. We define AT of V to be A of TV, or rather A times TV. It's an exercise just like in the previous case. Check that AT is a linear transformation. So, straightforward check, and I will leave it as an exercise. Right. So, let us look at an example. So, let us take a vector, let us take a linear transformation S from V to itself, be S of V being equal to say A1V. It is a dilation by A1, and let T from V to itself be TV is equal to another dilation. Does not need to be a dilation, it could be any linear map, but for the sake of this example, let us look at say S from R3 to itself, given by S of any vector V is say 3 times the vector, and T is the vector which is dilating it by say 6 times. So, T of V is 6 times V. Then what is our S plus T? S plus T of V by definition is SV plus TV, which turns out to be A1 plus A2 times V, which is a dilation again. We know it should be a linear map, but in this case it turns out to be a dilation itself. Similarly, we can talk about they are straightforward concepts, so let me not spend too much time on the examples. The thing, however, which I would like to note is that, so let the space of all linear transformations between V and W. Let us denote the space of all linear transformations between V and W be denoted by L of V comma W. Then the first thing to observe is that every linear transformation in particular is a function from V to W. So, hence then L of VW is a subset of the familiar vector space f of V comma W. Recall that f of V comma W is the vector space of all functions from V to W. Here the addition is defined in the most obvious manner. You take f and g here, f plus g of any vector v is fv plus gv, and a constant times f will be exactly like how we defined a minute back the scalar multiplication of a vector and a scalar and a linear transformation. The way we defined it, exactly similar manner we can define the scalar multiplication fv of w. And we have realized L of v comma w as a subset of this vector space vw. And further, what did we show? We showed that if you take two such linear transformations and add it, you get back a linear transformation. If you look at the scalar multiplication of a scalar and a linear transformation, you get back a linear transformation. So this prompts us to write down the proposition that the set L of V comma W is a subspace of f of V comma W. So the proof is quite checked already. We just checked that L of V comma W is closed under addition and scalar multiplication, and by lemma or a proposition which we have proved earlier, L of V therefore turns out to be a vector subspace of f of V comma W. In particular, L of VW is a vector space. So that is something. So we get from this proposition, the space of all linear transformations from V to W is a vector space. All right. Not only addition and scalar multiplication, we are also familiar with the notion of multiplication or product of matrices. When can we talk about the product of matrices? Suppose you start off with an L cross M matrix and an M cross N matrix. We can look at the product and obtain an L cross N matrix. So we would like to have an analog. So I have not yet described or discussed the relationship between the addition that we have just defined of linear transformations and the addition of matrices, but we will be coming to that in a minute. Before that, let me talk about product of linear transformations. So let S be a map from V to W and T be a map from U to V be let linear transformation between vector spaces U, V and W. Between vector spaces. Then we define the product of what? Product of ST, which will be now from U to W to be the usual composition. So this can also be written, we define the product or composition, the more familiar notion of composition from set theory. This is the same. This is defined to be ST of U, let me not put brackets unnecessarily, U is defined as S of TU for all U in capital U. Right. So this is the usual notion of composition of functions. In our case, we would also like to call it product of linear transformations, the product of linear transformations. Alright, so it's time to now talk about how these notions we have just defined of addition, scalar multiplication and of product, how does it gel with the notions of the addition of matrices, product of scalar multiplication of matrix with a scalar and product of matrices. So to do that, let's fix an ordered basis of, so we'll restrict our attention to finite dimensional vector spaces. So let V and W be finite dimensional vector spaces we would like to talk about the matrix associated to it, right? So finite dimensional vector spaces are essential as a hypothesis. And not just that, let's fix an ordered basis of V and W. And suppose beta equal to V1 to Vm and gamma equal to W1 to Wn. Yeah, note that generally, yeah, we'll keep track of the m and n very carefully. What we have effectively told is that our V is of dimension m and W is of dimension n. Okay, that's what we have just said. So suppose we start off with two finite dimensional vector spaces V and W, and we fix ordered basis for V and W respectively. Further, let S from V to W and T from V to W be linear transformations. Now, the moment we have a linear transformation from a finite dimensional vector space to another finite dimensional vector space, we can talk about the matrix of the linear transformation once we have fixed the ordered basis, right? So here we have S and T linear transformations, two linear transformations from V to W. We also know that S plus T is a linear transformation from V to W. Now we would like to know what is the matrix of S plus T with respect to beta and gamma. Then theorem, okay, let me start off with a statement like this: proposition. This is indeed a proposition, and we will be proving that. Then the matrix of S plus T is actually equal to the matrix of S with respect to beta gamma plus matrix of T with respect to beta gamma. So let's prove this statement. So what is our matrix of S with respect to beta gamma and the matrix of T with respect to beta gamma? Let's give it some names. First of all, let S be equal to, say, A11. Remember, this is a linear transformation from an m dimensional vector space into an n dimensional vector space. So this is going to be A11, A21, AN1, A1m up to ANM. Alright, and T beta gamma be equal to B11 to B1m, Bn1 to Bnm. Okay, so we know this is with respect to beta and gamma. So we know that T V J is equal to, the jth column will come into the story. So here we know that then SVJ is equal to, the jth column will come in, that is A1J W1 plus A2J W2 plus dot 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 AMJ NJWN. There are n basis vectors of W, it's an n dimensional vector space. Similarly, we get TVJ will be B1JW1 plus dot 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 BNJWN. So now let's look at what is S plus T of Vj. By very definition, it's going to be SVJ plus TVJ, which is going to be A1j W1 plus up to ANJ Wn plus TVJ. What is TVJ? B1j W1 plus BNJ Wn. Now we can do all the necessary rearrangements and finally obtain this is A1j plus B1j W1 plus up to ANJ plus BNJ times Wn. So we have obtained the jth column of the matrix for S plus T, and therefore the jth column is going, the first column will look like A11 plus B11, A21 plus B21, AN1 plus BN1. Jth column will be similarly written, and finally the mth column will be A1m plus B1m, ANM plus BNM, which is exactly equal, this matrix is exactly equal to A11, A21 up to AN1, A1m, ANM plus B11 to B1m, BN1 to BNM, which is equal to S beta gamma plus, did I write it wrong? Yeah, this is S beta gamma plus T beta gamma. So we have proved the statement. I will give it as an exercise to check that something similar can be concluded about the scalar multiplication as well. So let T from V to W be as in the be a linear transformation as in the theorem above. Yes, so as in the proposition above. And suppose A is a real number, then A T beta gamma, the matrix of A T with respect to beta and gamma, this will turn out to be A times the matrix of T with respect to beta gamma. So I will leave this as an exercise for you to check. The proof runs in a similar flavor, and I would advise you to strongly work out the details. Alright, so we have now talked about what the matrix or how the matrix associated to a linear transformation behaves when we add two linear transformations. We have also given, of course, as an exercise about how, if you look at the scalar product of a scalar with a linear transformation, how does the matrix corresponding to it behaves. Now we would like to now explore how the linear transformation. We would like to now explore how the matrix of a product of linear transformations behave. So for that, let me write down a proposition and directly tell you what the expected outcome would be. So to talk about product of linear transformations, we need to start with three vector spaces. So let U, V and W be finite dimensional vector spaces. Again, we are going to associate matrices. So let them be finite dimensional vector spaces. So as you can see, we have not talked about U, V, W or U, V in the previous case being finite dimensional till we wanted to talk about matrices associated to these linear transformations. That is to tell you that these notions are not necessarily defined only in finite dimensional cases. We can talk about the sum of two linear transformations in an infinite dimensional vector space as well. We can talk about the composition in infinite dimensional vector spaces. Maybe after this proposition we will give you an example in an infinite dimensional case. Right now let us focus however on finite dimensional cases, just so that we can see how the product and the matrix multiplication are related. So here we fix three bases, ordered bases for u, v and w respectively. So let us fix that, and suppose alpha, which is equal to say u1 to ul, beta, which is equal to v1 to vm, and gamma, which is equal to w1 to wn, be ordered bases of u, v and w respectively. Then the proposition states that if S from v to w and t from u to v are linear transformations, then in particular there is a matrix associated to both S and we have ST. As you can see, this is a linear transformation which we have already checked, or have we checked? Oh, we have not checked, but that's actually a simple check. So I would just like to give an exercise here. Prove that ST is a linear transformation. If you talk about composition of two linear transformations, you are not going to get some arbitrary function, you will again get back a linear transformation. Maybe we can work it out here, but before that, assuming that this is assuming that you have done the exercise, ST, which is a linear transformation, will have a matrix representation with respect to what? Let us just try to analyze where our map ST is from. T is a map from u to v and S is a map from v to w, and therefore ST is a map from u to w. What are the bases in u and w? Alpha and gamma. So we would like to talk about the matrix of ST with respect to alpha and gamma. This turns out to be the matrix of S with respect to what is S, where is S from? S is a map from v to w, and therefore this is going to be from beta to gamma and times T from alpha to beta. So I would like to note at this point that the operations of product, this is not necessarily a commutative operation. So in other words, ST is not equal to TS. In fact, TS need not even make sense if the vector spaces v, u, v and w are not suitably picked. It's almost the same case with the product of matrices, right? If you look at matrix which is say 1 cross 2 and matrix which is 2 cross 3, if you multiply you will get a 1 cross 3 matrix. However, you cannot look at the commutative version of it. So if A was the 1 cross 2 and B was the 2 cross 3 matrix, then AB makes sense, but BA doesn't even make sense. So that goes here. So the product of S and T is in this order. So before we go further ahead, I would like to give you an example of the fact that the product ST need not be equal to TS even in the finite dimensional case. Of course, if you already prove this proposition, then we are through. We know that there are matrices which do not commute, and for each matrix we can talk about linear transformation, and therefore we will get hold of linear transformations which do not commute. But before going into all these propositions, let's just give an example to indicate that in the infinite dimensional case also this is not true, and even if the domain is from the linear transformation is from the vector space to itself, even then it doesn't make sense to talk about commutativity. Why? Let's look at an example. So let U be a map from, say, R infinity to itself. Remember, R infinity is the vector space of all sequences x1, x2, x3, infinite sequences. So let's define U of in fact, let me call it something else. Let me call it the left shift. So let me call it L. I hope I'm not going to confuse you. L of, say, x1, x2, dot, dot, dot. This is the left shift. Let this be defined to be, we have seen this example. This is the linear transformation L that we would like to define. Check that this is a linear transformation. And R be the right shift operator. This time R is not the range, R is the right shift operator, which is defined as 0, x1, x2 and so on. Then check that LR is just the identity map. This is just x1, x2 dot dot dot. And what is RL? You should check that RL of x1, x2 and so on. First, it will do a left shift by throwing out x1, and then it will do a right shift, and therefore you will be ending up with something like 0, x2, x3 and so on, which is not the same as LR of x1, x2 so on if x1 is not equal to 0. Alright, so we have a straightforward example of when two linear transformations don't commute with each other. That's further established by this proposition, which tells that if you have the product of two linear transformations, and if you look at the matrix corresponding to it, it is going to be the corresponding product of the matrices. So let's go ahead and prove this proposition. So proof of the proposition. It's more or less keeping track of the indices that will give us the proof. So let's quickly go through the proof. So recall that alpha is equal to u1 up to ul, beta is equal to v1 to vm, and gamma equal to w1 to wn be the ordered basis of u, v and w respectively. And remember that S is a map from V to W, T is a map from U to V. So let T is a map which is from U to V. So this will be alpha to beta, or rather alpha beta. Let this be given by, let's put it in the matrix notation, A11. So our U is of dimension L, and V is of dimension M. So this is going to be AM1 to AM. So this final one would be for the Lth vector. So this is going to be A1L to AML. Be the matrix of T. So then we can write in compact notation. What can we write in compact notation? T U I. This is equal to, that will be given by the jth column there. that will be summation, sorry, that will be the ith column there. That will be A J I V J, right? Okay. Similarly, let's give some give the matrix representation of S. Now, S is a map from V to W. V has an ordered basis beta, W has an ordered basis gamma. So, this, let it be B11 to B this is thing from V to W. W has dimension n, so this will be n1, and there are L such vectors, sorry, M such vectors, this will be P and M. So, please do check that the indices are making sense. After all, the dimensions of V and W are clear. So, this is right, and this particular matrix representation tells us that S V j is equal to summation, that will be the jth column, right? The jth column would be B k j W k, where k is going from 1 to n, and here j is going from 1 to m. Alright, so now let us try to see what are we trying to do? We are trying to show that ST, we are trying to show this, we are trying to show that ST alpha gamma is equal to S beta gamma times T alpha beta. So, let us look at what is ST of uj. To talk about ST of alpha gamma, let us look at ST of uj. Uj will be S of, by definition, Tuj, but we know exactly, let us call it Uy, so that our indices do not get confused. So, we know exactly what Tui is. This is equal to S of summation j is equal to, just bring it up so that you can see it, this is equal to 1 to m A j I V j. But we know that S is a linear transformation, and therefore, this is equal to summation j is equal to 1 to m S A j I times S V j. But we also know what S V j is from our matrix representation. This is nothing but summation j is equal to 1 to m A j I summation k is equal to 1 to n S V j is B k j W k. And there we are in good shape now. Why? Because this is a finite sum. We can write it as summation A k, summation k is equal to 1 to n, summation j is equal to 1 to m B k j A j I times W k. So, what we will do is we will define C k I to be, let C k I be equal to summation B k j A j I, where j is equal to 1 to n. You should already start seeing the similarities with the matrix multiplication. So, this is nothing but summation. So, what is nothing but summation? ST of ui. So, let me just write that here. ST of ui is nothing but summation k is equal to 1 to n C k I times W k. So, what is the matrix of ST? Hence, the matrix of ST with respect to alpha gamma, this is nothing but C11 to Cn1 C1L to Cnl. I would like to leave it as an exercise right now to check that by your familiar notion of the product of matrices, check that B11 to Bm1, Bn1 to Bnm, this times A11 to Am1 here, A1L to AML. This is equal to C11 to C1L, Cn1 to Cnl, and therefore we are done. In next video we will take the story of how matrices and linear transformations play along with each other further. Yeah.